Hi, everyone. Today, what we're going to work on, you can see the title at the top of the screen. We're going to get into a review of rational numbers. Now, I'm not sure in terms of background how detailed we got in your discussion of rational numbers, but I assure you, everything that we're going to do today is a straight review from the past. Now, there might be a little extra kind of pressure that I'm going to put on you today of we're going to do all of our work today without a calculator. So I will give you a little concession of this may not entirely be review in terms of process, but I guarantee to you there is no new theory about rational numbers that is being introduced. We may have some new terminology, we may have a little bit new notation, and maybe we end up having some new ways to try some things. But today we're going to cover a pretty exhaustive review on number forms dealing with rational numbers. So what you see on the screen right now then is a formal definition in red and green for what a rational number is. And you can see in red that it's numbers that can be written in the form m over n, where m and n are integers, with n not being equal to 0. And that's what you see there is a does not equal symbol. So they have to be numbers in the form something over something, where both of those somethings are integers, and the bottom something can't be 0. So given that we've already addressed a full review of integers, we should be good to be able to kind of map out a few things dealing with rational numbers. Okay, the first thing that I want to make sure we can deal with is that whole restriction on the end, that n cannot equal 0. And so what I want you to get in your notes right below that definition is that blue question that I just asked. Like I want us to be able to put down, okay, why can't n equal 0? Okay, we need to consider that a little bit. And this may be kind of a weird conversation for us, but we're going to have it virtually. What I want you to imagine right now is that we were going to deal with some division. Why division? Because if you look back up at what I just highlighted, your rational numbers include a division operation. M divided by n, something divided by something. So we need to consider division. And what I'm going to ask you to do is we're going to make up a very simple division question. Let's deal with something pretty straightforward, and let's address maybe something like 6 divided by 2. Now, I want to give us a context for what we're talking about with division, just so it's not some theoretical thing, but that it's very practical. You're likely sitting at a desk, a kitchen table, you're sitting on a couch, I don't know, wherever you are sitting, I want you to look ahead on your desk, your table, your lap, and I want you to picture 6 things. Let's go 6 pens. And I want you to see those 6 pens sitting in front of you. You are visualizing 6 pens. And what I'd like you to do is I'd like you to break up those 6 pens into 2 groups. Okay, how many pens are in each group? And you say 3, and I say, congratulations, you know what division is. That is our division process. And so now what I want to do is I want to come back up to that restriction, that restriction about n not being able to equal 0. But maybe we'll look at it in a different context. If rational numbers are m over n, where the bottom can't be equal to 0, well then, why is the top allowed to equal 0? So let's jump in and let's examine what happens if the top equals 0. Okay, I have 0 pens sitting on my desk, and I decide to break that up into 2 groups. How many pens are in each group? And hopefully we're fine to get a value of 0. Because you started with no pens, then that means that when I break them up into groups, I still have no pens. That's why whenever we have a fraction, where the top is 0 and the bottom is like a non-zero, any other number, then the value of that fraction is 0. Since I started with nothing, I finish with nothing, is a way that you might think about that. Okay, let's look at the case now that we've highlighted, this whole restriction that the bottom can't equal 0. So let's flip it then. I have 6 pens. You can see them on your lap. You can see them on your table. And I'd like you to break up those 6 pens into 0 groups. How many pens are in each group? I'm imagining that some of you would have a pretty weird look on your face right now. Because how do you start with 6 pens and break them up into 0 groups? Now, I will say this. I will have a bunch of people that if I said, okay, well, what's your answer to that question? You might tell me 0, of which you're going to tell me you have 0 pens in each group. And I'm going to go, no, you don't. You have 6 pens sitting on your table. Okay, so it can't be 0. And then I might have some people say 6. And I'm going to say, yeah, but if you have 6 pens, then that is 1 group of 6, not 0 groups of 6. Oh, shoot. So it can't be 6. That puzzled look I was talking about is a good thing. How do you start with something, 6 pens, and break it up into 0 groups? You can't. If you start with something, then there must be at least 1 group of it, or parts of groups if you want to think about magnitude. Therefore, our answer to this question in your mind might be something like, I don't know. I don't know what that answer is. Okay, I don't know is not going to be a very formal answer. I don't think can't do it would be any more formal. What your solution to that question is actually the word undefined. That describes to your reader that you cannot make that calculation. And that's why if we ever start with a non-zero and we try to break it up into 0 groups, we get an undefined answer. Okay, so hopefully we can take a peek back at that rational numbers expression and we can now see the full detail to it. Any rational number is a number that can be written as an integer divided by an integer, as long as the bottom does not equal 0. The top's okay to equal 0, the bottom cannot equal 0. Okay, let's jump in and start doing some stuff now. I think we've had a decent talk in terms of theory. Here we go. Okay, what I've put on the screen is a little bit of fraction form. And I've given you your 3 forms of numbers that can include fractions. What I want you to do is I want you to take a shot and see how much you can remember from way back maybe of what would be the names of those fraction forms. So I want you to give it a shot, see what you can come up with. Okay, pause the video now, try to get out the names. Okay, we're back. I'm hoping that we took a look at the first one and we knew that that was called a proper fraction. Why is it called proper? Because my top number, my numerator, is a smaller number than the bottom, than the denominator. If my top is smaller than the bottom, I have a proper fraction, and that is what then leads us to an improper fraction for the second one. My top has a larger value than the bottom. Now, I need to be very, very careful and very, very exact in my wording here. I know that for a lot of you, you're coming into this course, and if you ever had an answer like 8/3 pop up, you would have been mandated, probably made to, change that improper into that last form. And I need you to know that 8/3 is a perfectly good solution. Perfectly good. I really don't like the name of that fraction form. Because when you call something improper, it makes it sound like that's not good. When there is nothing wrong with you having an expression with a value of 8/3. So we'll get used to working through that this year. Your last number form, hopefully we have that is a mixed number. Sometimes you can hear it described as a mixed fraction. I don't personally like mixed fraction because there's nothing mixed about the fraction. It's a number that has mixed forms. It has your integer in 1, and then it has your fraction component in your 4/7. Okay, those are your 3 number forms for us. The forms that deal with fractions in them. We have to be comfortable to work our way through them. The last new thing that I think we need to pop up is, since we dealt with our full integer review yesterday, it's important for us to note that we can also have negative fractions. So it's not a new number form. However, as soon as we start to deal with negative fractions, an issue may arise. We have 3 forms for negative fractions. You could tell somebody that you had a fraction of -6/2, for instance. But that could also be 6 divided by -2. I just want you to notice that gold expression and the blue expression both equal -3. So those are the same thing. Versus what we could have is 6/2, and that value is negative. I want you to notice that what has happened in all 3 of those fraction forms is just that I'm moving the position of the negative. We should all be okay to do that. Take a look at your gold form. Isn't a negative divided by a positive a negative value? Look at the blue form. Isn't a positive divided by a negative value? Look at the red form. Isn't a positive divided by a positive then made to be a negative equal to the same as the gold and the blue? So all 3 of those forms are equal. The problem is one of them is horrible form. I want you guys to zero in on the blue. We should be good, given our previous discussion about what does it mean to be a rational number, that blue version doesn't make sense. It doesn't make sense. I want you to take your 6 pens that you see on your table, and I want you to divide them up into -2 groups. Now, how do you get a negative group? And so because of that, little rule for us, we can never, ever, ever have our denominator be a negative. So let's say you work through a problem and you get to that blue solution. You have 6/2. Well, you're obviously going to calculate that to an equals -3, so it's not an issue. But what if instead that problem was a 7? Now, you have to leave your answer in fraction form, but you realize that 7/2 is a horrible form. Well, you have 2 options. What you can do is you can move the negative. That is, from the bottom, move it to the top. We just discussed a negative divided by a positive is the same as the positive divided by a negative, so feel free to rewrite it in the gold form. Or make the whole fraction negative. So take your red form, and say that you have 7/2 and make sure that that negative is right on your fraction line. Okay, I think we've got everything for fractions now. What I want to do is I want to spend some time jumping in between number forms. So let's take a look at our next section. Okay, you've had a bunch of theory thrown at you. Let's jump in and work our way through actually some converting. So I want you to copy down question 1 that says convert to improper or mixed form. So what we are going to do is we're going to take every single one of these fractions. If it is an improper, we switch it to mixed. If it was mixed, we switch it to improper. And again, we're doing this with no calculator. Okay, what I want you to do is I want you to pause the video and try to get solutions to all 5 of those. Okay, you hit a snag, well then you can push play again and we can catch up a little bit and we can find our mistake maybe or work our way through some struggle. And then I want you to pause it again and try to get out ahead of me every time. Okay, so I want you to try to come up with a solution for those 5 and then we'll meet up in a second and we'll walk through each one. Okay, pause it now. Okay, we're back. So now we're just kind of looking and seeing, okay, well, how much do I remember about working with my fractions? The biggest part that I would hope that we can kind of get into is that each one of those fraction lines is really just an operation, remember. Remember, that's division. And so really, all that you're being asked to deal with in each of these cases is to consider division. So I'm just going to get rid of all those circles on my division, and I'm going to actually divide. So if I take a look at A now, I'm going to focus it on 5/4. We probably have a little bit of an algorithm. Remember, that's just a process where we look at that and we might say, okay, how many times does 4 go into 5? Well, I can at least get one group of 4 in 5. Not exactly. So what do I have left over? Well, I would have 1 left over. And what sized bits were those? Those were quarters. So I have 1/4 left. So hopefully we got down to 1 1/4 and we match up. Let's jump into B. So as I go to jump into B, if you struggled on A, you should be pausing it right now and try and be on your own. Okay, don't ever lose an opportunity to give something a try on your own. Okay, we're working our way through B. If I recognize that that's 23 divided by 5, that's all that says. Well then, how many 5s can I take out of 23? I got 4 of them in there. Why? Because 4 times 5 was 20. That leaves me with 3 more to get up to 23, and my size bits were fifths. So 4 3/5. Okay, if we've got that, I think we're probably pretty solid at being able to change improper fractions to mixed numbers. Now let's take a look at C, because we are being asked to go in the opposite direction. I would bet that I would have a bunch of people that learned an algorithm in question C, that you were taught a process that might sound something like this. Okay, I have 4 2/3. So the way I change that back to an improper is I take my 3 and I multiply it by my 4, by my big number, my whole number, and then I need to add that on to the top. So if I have 4 2/3, then I have 4 whole groups of thirds. So that's going to be 12 of them. Add on your 2, that gets me to 14. 14 what? Well, my size bits in this case were thirds. There we go, 14 thirds. I'm just going to warn you a little bit that gold algorithm that you see with my arrows and my operations, it can get you into trouble sometimes. So be very careful. Okay, question D. I've got 7 2/9. If I need to change that into an improper, then I need to take my 7 times my 9. That's going to give me 63/9. I then have that extra 2, so that gets me up to a 65. 65 what? My 9ths. Hopefully we match up on those, and hopefully we feel pretty comfortable with that. Okay, I'm going to bet and say I've got a few people who have an incorrect answer on E, because we put so much faith in that gold algorithm. If I was to blindly follow those gold arrows, then this should be my answer. 4 times negative 5 is a negative 20. Add on my 3 is negative 17/4. And we all match up, right? No, you should not have negative 17/4. So what makes E different than C and D? Okay, I'm hoping that negative out in front is screaming at you. So, where did I make my mistake? It was in blindly following the algorithm. Maybe you guys know, if not, this may be brand new theory to you, that really what negative 5 3/4 means is that you have 5 3/4 and it happens to be a negative value. There's actually hidden brackets in that expression. Math people are lazy. They don't want to write stuff that they don't have to. So we all agree, the whole mathematical world got together and said, hey, if we have a negative mixed number, there's really brackets around the number portion. So really when I change that, I have my 5 times 4, which gives me my 20. I have to add on my 3. I have an extra 3/4. That means that is a 23/4 that just happened to be negative. So remember, you give me that form, you give me that form, don't you dare tell me that. And there we go. Okay, hopefully changing improper to mixed, mixed to improper went okay. Let's jump into another section. To do that, I want to go back and I want to talk about our definition for rational numbers, just really quick. Because there is another way to identify a rational number. And what it requires is everything we just talked about. The operation that's in our fraction, our division. That there are a lot of ways that you can identify a rational number, but they might not always be in fraction form. So, I'd like you to get down one other little note. If I ever take an integer, and I divide it by an integer, then I will get a decimal form. Now, that decimal form might be a whole number, or it might be something really ugly. But that decimal form is a repeating decimal. So you end up getting the same decimal places that repeat and repeat and repeat. Or it terminates. And what we mean by that is it ends. It doesn't go on forever and ever and ever. It stops. You have an exact value as a decimal. That sometimes changing rational numbers in fraction form into decimals, we can lose the definition of a rational number. Now we can look at it in decimal form and we can say, yes, okay, it is a rational number because it repeats or it terminates. Okay, let's jump in and deal with that process then. So now you take a look at question 2, and you should be copying down question 2 in your notes. What we're going to work on now is converting to decimal or percent form. We have spent the previous part of today living within one form that numbers can take, fraction form. Well, we have 2 other number forms, that being decimal, that being percent. And so what we're going to do is we're going to now jump between our number forms. If you take a look on the screen right now, you will see 4 fractions. And so they were all presented in one form. And what we want to do then is we want to jump into the other forms. Now, part of what we're going to go through today in this section is probably going to be new to you. Some of what we are going to do right now might be stuff that you haven't looked at in a while. The large reason for that is you've probably been using a calculator an awful lot. And I need to motivate you to throw that calculator away. Now, I don't literally mean throw it away, but I mean set it aside. That calculator is not the first thing you reach for. that by the time you were sitting in our grade 12 advanced functions or calc course, you hardly even use that thing anymore. So if you have become very calculator dependent from the past, I'm going to tell you it's not your fault. However, I need you to not be stubborn and want to hold on to it. That also means, though, that if I'm going to ask you to do more and more without your calculator, then maybe I got to show you some ways that you can work without your calculator a little easier. And so that's going to be part of what we're going to deal with right now. Okay, you should have got down those 4 questions, and we're going to work our way through together on these ones. Okay, this is a together. Okay, we take a peek at question 2A. You have to convert 3/4 to a decimal, then a percent. Okay, I want you to get a solution to A and A only. Okay, pause the video now. Okay, we're back. So, I'm hoping that everybody knew what 3A was, that you know what 3/4 is as a decimal or a percent. Like you just know it because the numbers are pretty direct. So maybe you say, hey, 3/4, like the way I even read that as money, 3/4 is 75 cents. So you already have it as a decimal, 0.75. Please do not read that as 0.75. I know that we understand that that is 75 100ths. 75 cents. How many cents are in a dollar? 100. It's 75 100ths. However, you have to please be very, very careful. Sometimes when you read decimal places and you don't read them digit by digit, it can actually mislead you in terms of how big something is. Let me give you an example. What if I was to throw down 0.8 versus 0.12? And I said to you, hey, which one's bigger, 0.8 or 0.12? Maybe you guys can see how that could be a little misleading by how we just read it aloud. Because 12's bigger than 8, so 0.12 must be bigger than 0.8. Let alone 0.92 versus a lowly 0.8. Well, in that case, it does work. So now you start to go, okay, when I read multiple digits, maybe that's a little confusing. So my recommendation to you, read them digit by digit. 0.75 versus 0.8. Now I hear the 8 versus the 7, and I know which one's bigger. Okay, we get down to that point, and I'm hoping we were pretty automatic with our percentages. 0.75 would be 75%. Okay, as I said to you, I am hoping that that was pretty automatic. However, what if you didn't know that was the case? Well, let's go back to what a fraction means. And a fraction simply means divide. So how about we do some long division? Now, I'm going to bet that a bunch of us haven't done some long division in a while. And I'm even going to pressure you to work your way through some short division as we go. But let's get down an example of long division, how I could work my way through this. I could say that I'm going to take 4 and I'm going to divide it into 3. And now what I'm going to do is I'm going to go through an algorithm to be able to calculate that. Remember, you don't get a calculator. So if I take that 4 and I divide it into the 3, I say the 4 is way too big. I can't even take one group of 4 out of a 3. So there are 0 groups of 4 in 3. Okay, well, that didn't get me anywhere. So what I can do is I can create a number that's a little more workable. Remember that I have a decimal place that comes after the 3. And I could put as many zeros after that as I like. 3.00000 is equal to 3. But those zeros might give me something more workable. So if I include one more zero, and I forget about the decimal place by copying it up above. Then really what I can do is I can say I have 30 divided by 4, and now I can take a 4 to that. How many 4s go into 30? 7 of them. Why? Because 7 times 4 is 28. And now I can find out what's left over, so I find the difference. 30 subtract 28, there's my 2. And notice, I could keep doing that as I keep going along. Some of you guys were taught this. Now bring down its friend. As you bring down like the next decimal place, the next place value. And we could continue that algorithm as we keep going. Okay, how many times does 4 go into 20? 5 times. Why? Because 5 times 4 is 20. And when I subtract, I have no difference. So I know I have an exact answer. And there is my solution. So hopefully we get down to 0.75. There is your decimal form. And now we can change that into a percentage, whatever you need to do. So long division may have been something that you got a little out of shape with. We'll get back into shape with that as we go. Okay, how do we end up dealing with our 0.75 decimal form to our green 75% form? Well, the question I could always ask is, what are all percentages out of? And that should be a pretty quick response that percentages are out of 100. So when I read my blue, I notice I have 75 100ths. And so therefore, I have my 75%. Okay, that is one way or a couple ways that you could have gone through A. Okay, we just spent a ton of time talking about something that should have been known or automatic. Let's start to get into some other things as we go. Okay, let's take a look at B, and we are going to walk through B together. First off, you notice that 7/3 is an improper fraction. So we have to turn that into a decimal, or we have to turn it into a percent. My judgment, my advice to you would be, if I have an improper fraction, a really good first step might be switch it into mixed number form. Make it a mixed number. And so pretty quickly I can go through and I can say, okay, I am going to take 7/3. That means 7 divided by 3. Okay, well 3 goes into 7 twice because 2 times 3 is 6. So I have one more third left over. And by me changing that into mixed number form, mixed form, I think we should be pretty good. For me to get my blue, that is my decimal form, I know it has to be 2 point something because my whole number is 2. Now it just requires me to know, well, what's 1/3 as a decimal? And I would bet that I got at least half of you that know what 1/3 is as a decimal memorized, because you've seen it so often. Now, this becomes a little bit of a form issue, so pay close attention. I would have a lot of people that would tell me, oh, 1/3 is 0.33. Okay, no, it's not. It's close to that, but no, it's not. I would then have some people that said, oh, wait a second, it's like 0.33333333 on forever. And maybe we remember how to write 0.333333 forever, how to write that in our notation. Now, I will have some people that do this, and I'm going to say, close. That's not the proper form for that repeating decimal. Keep in mind that what is repeating is the decimal 3. That 0.3 is repeating. So the way we mark a single digit that repeats is we don't put a line over it. We put a dot on your single digit. So 2.3 repeated. There we go. Okay, if we have to now change that into a percent, well, I don't know how we deal with that as a percentage. We could work our way through the last, which is, well, when I can make it out of hundredths, then I can change that into a percent. So what might be functional for me might be to say, well, that's a 2.33. That at least gets me into the hundredths. The problem is I think we can see that because those 3's repeat, we're going to have to round this off. And you will have to round it off. For us to get our percents, if there are no inherent rounding rules, we round to 2 decimal places. And so what we then need is we need our amount out of 100 and our 2 additional decimal values. Now, some of you guys learn that if you ever want to change a decimal into a percentage, you multiply that by 100. And the shortcut to multiplying by 100 is to move the decimal place 2 spots. I would have a bunch of you that would have memorized that process because you've done it so much, and you would write down 233.33%. And there we go. Now, here's where we get into a bit of a form issue as well. That's technically incorrect. Not your number, but your form. I want you to notice that 2.3 repeated is not exactly equal to 233.33%. It's not exactly equal, but that's what your line says. It says equals. So the way that we denote that there has been rounding that has occurred is we put a little dot above our equal sign. That tells your reader you rounded from the previous line. There we go. Okay, hopefully not too bad. And some of this stuff is coming back to us. I'm going to make a little wavy line here. And maybe we're getting to the point where we're like, oh, okay, like I never knew that before. And we're expanding what we have. Okay, let's jump into C. Everybody in here knows they can do long division. But I'm going to guess that none of you have 11ths memorized as decimals. Like, I would expect you to have halves memorized. I would expect you to have thirds, quarters, and probably fifths. But 11ths? I don't think you know what 11ths are as decimals. So this is where I want to maybe add something in. 5/11ths. Here's a little trick. Ask yourself, what would you add to 11 that gets you to 20? So we come up with 9. Then I'm going to tell you, multiply that top by 9. So what would you add to the bottom to get you to 20? Multiply the top by it. And so we may then go, oh, so like my decimal is like 45. And I'm going to, well, not quite. It's 0.45, but not quite. I'm going to go through something super, super fast. I'm going to do a little long division. I'm going to take 11 and I'm going to divide it into 5. And I'm going to go fast. Okay, it goes in 0 times, so I bring down the next 0. I have 50. 50 divided by 11 is 4, and that gives me 44, which gives me a difference of 6. Bring down the next 0. Well, 11 goes into 6 5 times, because 5 times 11 is 55. That brings down a 5. Bring down the next 0. 11 goes into 50 4 times, because 4 times 11 is 44. That's a 6. And some of you are starting to see the pattern. So if we take a look at that blue then, we can state, oh, wait a second, it's 0.45454545. So it's 0.45 repeated. And this is where some of you learned about that line in the past. That I use a line as my repeating symbol when I have multiple digits that repeat. So use that as a bit of a trick. What would you add to 11 to get up to 20? Do the same thing to the top, or multiply the top by that. We just need to remember that it's a repeating decimal. Okay, if we have that, then we should be pretty quick to be able to turn that into a percentage. You can multiply that by 100 or move the decimal place 2 spots, and we should get 45.45. And I know I'm right because the next digit would have been a 4, so I don't have to worry about my rounding. Put put on my percent, but mark it as an approximate because I did round to get that green percentage. Okay, let's try the last one. I don't know how many of us have ninths memorized. I would expect no one to. Well, let's use the same trick. What would you add to 9 that gets you up to 20? Multiply the top by it. So you would say you'd add 11, so I multiply my top by 11. Now I just have to remember that that's going to repeat. So I'm going to get a 0.44 repeated. And then I'm going to go boo. If 44 repeats, 44, 44, 44, 44, oh, then it's not 2 digits that technically repeat. It's technically 1. So I have a dot above my 4. I can get rid of all that green. There is a trick. So that's just a trick that I've come up with over time to remember how to change 11ths and ninths into decimals. Please don't think that that works for everything. Like if all of a sudden I went and I gave you like 5/13 and you go, well, what would you add to 13 to get you up to 20? I multiply the top by 7. No, you can't do that. But it is something that's pretty functional. It might be a nice thing to use. Memorize it for your 11ths and ninths, and that'll help you out. Okay, last thing we can do is change that one into a percent form. That's a repeating decimal. I'm going to have to round, so there's my approximate, and I get 44.44%. Okay, we have covered a lot of stuff. We're going to keep it going. Here we go. Take a look at E. I think we should be pretty good now to throw everything in together. So I'm going to pick up the pace and we're going to work together on this one. Okay, the first thing is I gave you a mixed number. We want to be functional. Let's change it from a mixed number. An improper fraction, I will change to a mixed number. So I'm going to take that 12 and divide it by 5. It goes in 2 whole times and 2/5. So I would hope that we would all be good to say it's 2 point something. And I would also hope that we know how much a fifth is worth. I would hope that we are good that 1/5 is equal to 0.2. If you didn't know that, it is worthwhile to know that. So remember that. That means if 1/5 is 0.2, then 2/5 is 0.4. Of course, you could always do 12 divided by 5 and do long division, or you could always do 2/5 now within long division and calculate. But if we remember that 1/5 part, I think that can be helpful. Change that into a percentage. That means we get exactly 240%. Notice, I don't have a dot above. We don't put dots on percentages. We put dots when we round, and I did not have to round in that case. Okay, I think we have an opportunity to try one on our own. So I want you to get a solution to F. Pause it now. Okay, we're back. So the first thing I'm going to do, change that into a mixed number. How many times does 3 go into 17? 5 whole times, because that's 15, which means I have 2 left over, 2/3. Okay, I can change that into a decimal. I know I got 5 point something. And I should be good that 1/3 was 0.3 repeated. So therefore, 2/3 is 0.6 repeated. Like I would have had a bunch of people that would have told me, hey, 2/3 is equal to 0.67. No, it's not. It's 0.6 repeated. It'd be 0.67 if we rounded. Okay, we get that. We can now change that. Well, since I have a repeating decimal, I'm going to have to round. There's my round. And I'm going to have 566 points, and now I will have like a 6, 6, 6, 6. I know I have to go to 2 decimal places, which means I need the third one. That third 6 is going to round up the second 6 to a 7. And so my final answer then is 566.67%. Okay, hopefully we got a little confirmation. Hopefully things are going pretty well on F. Okay, we're going to keep it going. We're covering a lot today in terms of number forms. Let's jump in and play around with probably your least enjoyable number form. I'm going to give you guys some decimals. And if I had to make an argument to you guys of what is the number form that you are least comfortable doing mental math with, I would actually put my money on decimals. That is, I'm hoping that a lot of you, when you see a fraction, you don't even think fraction. You just think that it's the division between two whole numbers. And for most of us, when we deal with whole number operations, we are so much faster than decimal operations. So we're going to take a look at problem 3, and I want us to take a bunch of decimals and work backwards in a way. We're going to convert it into an alternate form. We're going to convert that into fraction form. Now, it may be a mixed number form at some point, but we are going to convert it into fraction form. Okay, let's take a look at A. I don't even know how much we need to cover A. I would expect every single person in here should be able to tell me that 0.5 is 1/2. However, I would like to talk about an algorithm that you guys can use that can make this process easier. When we move into B, I would expect some of us to just know what B is. But take a look at C and take a look at D. I don't expect us to know those off the top of our head. So how can we take a generic decimal and convert it? Well, one of the things we can do is we can use place value. So you take a look at your 0.5, and when I have 0.5, that last decimal place, I can examine its place value. And we should be good that that 0.5 is in the tenths column. So if I had to ask you, do fractions have decimals? You should tell me no. It is horrible form if I have a decimal within my fraction. So take 0.5 and get rid of the decimal. So it's just 0.5 or 5. Now examine your place value. That 5 was in the tenths column. So write it over 10. Now you just notice that that green fraction can be reduced to lowest terms. And so you're going through the process of dividing the top by 5 and dividing the bottom by 5. Please don't write that red down. You guys do that out of reflex so much. Just do it. Don't write it down. If you knew enough to write it down, then just do it. But that's what we're doing, dividing top and bottom both by 5. And we then come in on our 1/2. So I just want you to notice that that green gives us a process to get there if we don't know it. The other thing that I want to draw your attention to is some people learn a different way, and I just want you to be very, very careful using this strategy. You may say, hey, fractions don't have decimals, so my top is 5. And now what I do is I write that over my place value, but with respect to my number of decimal places. So I have a 1, and I look back and I notice that 0.5 is in the first decimal place, so that means I only put 1 0. The first spot, so I put 1 0. And now I can reduce it and I get my 1/2. I'm just going to tell you, be very careful. You might find if you use that as your algorithm, you might fall into a trap. Okay, let's keep going as we go. So you take a look at problem B, and I would expect, given what we talked about in the last section, that I would have a bunch of people that could tell me right now that that is equal to 2/5. Because you know that every 1/5 is equal to 0.2, so 2/5, there's my 0.4. Done. However, if we wanted to use an algorithm on it, what we can do is we can say that 4 is in the tenths, so fractions don't have decimals, so get rid of the decimal, write it over its last decimal place. Now I get that, and I can reduce, and I can divide top and bottom both by 2, and there is my 2/5. Okay, let's take a look at C. C is not one that I would expect you to have memorized. So process for us would be, I can get rid of my decimal because fractions don't have decimals. So my top becomes 36. Now I take a look at my last decimal place, And that's in the hundredths column. So I write that over 100. Okay, or I would have some people that would say, hey, get rid of the decimal. 2 decimal places means 2 zeros. In either case, we come in on 36 hundredths, and now we have to reduce that to lowest terms. So what I want you to do, pause it here, reduce that to lowest terms. Okay, pause it now. Okay, we're back. So hopefully we took a look at those and we said, hey, I can divide out the top and bottom by 4. Now, maybe we looked at the top and bottom and said we divided it by 2. And so maybe you said, hey, that's an 18 over 50. And then you realize that there's still even numbers. And I'm just going to tell you, try not to bail out just on the even number feature. That maybe we can look at that and try to be a little more efficient with that reducing. And instead of dividing by 2, then dividing by 2, we could take the original and divide by 4 and go straight to lowest terms. Okay, I think it's time for us to start one on our own. So what I want you to do is to tackle D start to finish. Okay, pause the video now. Yeah, okay, we're back. So the only functional part for us, fractions don't have decimals, so get rid of your decimal. That 5 is my last decimal place, and that would be in the thousandths column. Now I'm taking that and I'm trying to reduce. I don't think that we are going to be automatically perfect in our reduction. Like at the very least, I notice both those numbers end with a 5 and a 0, so I know 5 goes in. However, like that ends with a 25 and that ends with 2 zeros, so like 100. Quarters go into that evenly. So I could divide out a 25. So I would at least say that if you divide it by 25, we're pretty solid. My top is $1.25. That's 5 quarters. My bottom is $10. So how many quarters would go into $10? And you're like, well, 4 quarters goes into $1. So if I multiply 40, and if we got there, I think we're doing pretty well, dividing top and bottom both by 25. But then you notice, shoot, I could divide out again. And if I divide top and bottom by 5 one more time, I get at my 1/8. So what was the best value to divide by? If I had actually divided by 125 at the very beginning, top and bottom, I'd be good. I just don't know how many of us can divide by 125 automatically. Okay, we got 2 more. I think these are both cases where we can start and go on our own. But I don't want you to get to F yet. So I want you to work your way through E, get a full solution, and then we'll come back and check. Okay, pause the video now. Okay, we're back. So this is the one that makes me nervous. And this is the one where I warned you earlier. If I use that green method and I say, okay, well, fractions don't have decimals, so let's get rid of the decimal. And now what I see there is 2 digits, so I write that over 2 zeros. I'm hoping you can see that you are wrong, but I would bet that I would have a few of you that made that mistake. That's where that algorithm gets you in trouble. Okay, the first thing that I want to draw your attention is everybody should be able to look at the green and know that they're wrong. Know that they're wrong. Because take a look at the relationship between the top number and the bottom number. 16 versus 100. That's a proper fraction. My top is smaller than the bottom. And I know when I convert a proper fraction, I have to get 0 point something. Because the top is less than the bottom, I'm less than 1. But when you look back at the original, you go, oh, shoot, I had 1.6. I was bigger than 1. So that's telling me I have to have an improper fraction. That's where that algorithm, that little trick of my number of digits, decimal places, represents my number of zeros can get you in trouble. If instead you just really focus in on decimal place. Okay, what decimal place is the 6? It's in the tenths. Well, then that ends up getting me 16 over 10. Now, if you're very focused, you would say how many decimal places? One decimal place, so over 1 0. Now you can reduce that, divide top and bottom both by 2, and there is our 8/5. Okay, I think we're ready for F. F's the last one for today. So you go start to finish on F. Okay, pause it now. Okay, we're back. So I think this one provides a good gauge for you. Our first line was probably something like that. The 4's in the hundredths, so over 100, or the 4, 8, 4 represents 2 decimal places, so over 2 zeros. Now I got to spend some time reducing. Okay, I take a look at top and bottom, and my focus is going to be that bottom, the 100, because I think about the numbers that go into 100. Well, the answer also ends with a 0. So that means that I know 2 goes in because 100 is even. 5 goes in because it ends with a 0. I am looking to try 2 or 5 into 384. Like, yes, I'm omitting the 10 because clearly 10 doesn't go into 384. It doesn't end with a 0. So maybe I start off with 2. And now what I'm going to do is I'm going to do a little division. This is our opportunity to talk about some short division. So we should be comfortable with long division. You writing 384 divided by 2 and slowly, methodically working your way across. How many times does 2 go into 3? Once. Why? Because 1 times 2 is 2. What's left over? Bring down the next digit. How many times does 2 go into 18? 9. Why? Because 9 times 2 is 18. I have nothing left over. Bring down the next digit. How many times does 2 go into 4? 2. Why? Nothing left over. There's my confirmation. I think we can do that problem with writing down almost none of that green. I want us to get to the point where that might be the only thing that we write down, where that's the only thing we write down. So how can we do it? Well, in this instance, I'm going to just write my 384 over here, nice and big, so we can see how we can work with that number. I am going to divide that 384 by 2. I've already made that decision up in my mind. So how can I do it? Well, I want you to look underneath the 384 100ths. That's where I'm going to write my answer. So the first thing I say to myself is, how many 2's can I take out of a 3? 1. And then I ask myself, how many left over? 1. And I put that little remainder, that left over, beside the 8, because I'm about to bring down the 8. Now, I don't actually write in the purple. I don't write in at all. But I have the remainder of 1 with my next digit of 8. There's my 1, 8, 18. So now I start that whole algorithm all over again with 18. Okay, how many 2's can I take into 18? 9. Why? Because 9 times 2 is 18. That means I had 0 left over. So I'm technically bringing down a 0 with the 4, but because it's 0, I don't even worry about it. Now I have 4 divided by 2. 4 divided by 2 is 2. There's my 192. Look at that. We just did short division. We hardly wrote anything down. If you're looking at that and you're going, I don't think I could do that, you can, because grade 9s prove it to me every year. Try it. You're going to goof up sometimes. There's no harm if we make mistakes day to day. There is no harm. Try it. And I think you might surprise yourself with how fast you get really good at short division. Okay, now that I wrote that 192 huge, I'm just going to write that a little smaller so my fraction doesn't become huge. Divide my bottom by 2 as well, I get my 50. Okay, I'm going to look at that 50 and I'm going to do a little factor tree on that 50. I'm just going to do it sideways. The numbers that I know that go into 50 would be like a 5 and a 10. 5 times 10 is 50. And then 10 is 5 times 2. So I take a look, and the only number that I should be looking at in 192 is 5. Does a 5 go into 192? Nope, because it doesn't end that way. Does a 2 go into 192? Yes. So I know that I'm going to take 192 and I'm going to divide it by 2 again. So I think we all have an opportunity to try another short division of 192 divided by 2. Give it a shot, see what you can come up with. Pause it now. Okay, we're back. So hopefully we take a look at it. The bottom's nice and easy. 50 divided by 2 is 25. Now my top. Okay, I start off with my 19. 19 divided by 2 is 9. Because 9 times 2 is 18. So that means I have 1 left over. I take that 1 and I put it together with the 2. 1, 2 is 12. 12 divided by 2, 6. I'm done. You take a look at that, we match up, and I think we're doing great. The fact that we divided by 2, then divided by 2, told us that we could have just divided by 4 and went all the way down to our final answer. So guess what we're going to do? We're going to take 384 and we're going to divide that by 4 using short division. Okay. I start to work my way through and I say, well, I can divide the bottom by 4 pretty easy. There's 4 quarters that go into $1, 25. Now I'm going to divide my top. So I take my 384 and I'm just writing it up here nice and big. How many 4s can I take out of 38? Well, 4 times 9 gets me to 36. That's the closest without going over. But when I subtract that, I'd be 2 short. So I'm trying to do how many 4s into 38? That would be 9, plus the additional 2. I got 2 left over. Bring that 2 together with the 4, so now 24. 24 divided by 4, 6. And it went exactly, so I know I'm done. There we go. Nice. Okay, we had a long one today. And I'm hoping that a lot of what we talked about today was pretty automatic for you. Like, I'm hoping that it was. However, I would guarantee that for a large number of you, there was at least a nugget in there somewhere where it wasn't just cold review and you knew all of that, but we knocked off some rust a little bit with some decimal and fraction and percent operations. But also, you maybe have a new little strategy or a new piece of information that can help you moving forward. Okay, your job now, jump in and get some practice. Okay, best of luck.